All right, today we're looking at solving linear inequalities. This would have been what we learned on the first day of Chapter 9. I'm actually looking at a problem here from the second day of Chapter 9, problem 914, because it starts off with a great review looking at 6 inequalities that we're going to solve. It starts off easy, and then it progressively gets a little harder, and it also shows us 2 unique cases at the very end that we want to look at specifically. So, when you're solving a linear inequality, it's going to start off by just solving it like a normal equation. All right, so I'm going to draw my line down the center. I'm going to get x alone. In this case, there's nothing to distribute. All of x is on one side already, so this first one's very simple. And we find that x is less than 5 at this point. And that's my answer here. There was nothing special about that one, nothing unique. I just can get straight to my answer. Now we do want you to graph it at the end. So we're going to draw ourselves a nice little number line. And I do very simple number lines with just 3 ticks. I put 0 in the center, and I put my reference point on one side and its opposite on the other side. And yes, I used a word called reference point. The value that we found here is known as our reference point. Another word for that is our boundary point. This reference point or boundary point marks the point that makes the change between solutions and not solutions, because what we see here is there's an infinite number of solutions that make this inequality true. As long as x is any value less than but not equal to 5, this inequality will be true. And we'll demonstrate that in just a moment here. All right, so let's go ahead and let's draw it on our draw our reference point or boundary point on the number line. And to do so, I'm going to look over here to see what type of symbol I'm going to use. And I see a closed symbol, closed dot is when it's equal to. And what I want here is actually an open dot because it's not equal to, it's just less than. So I'm going to put an open circle, an open reference point at 5. And then this symbol also tells me which direction to go if x is on the left. X should always be on the left because that's our focus here. X is what we're talking about. And so when x is on the left of our statement, my symbol actually points at the direction you're going to be going, because less than is to the left of that reference point or boundary point. All right? And this is basically marking off all the numbers that are solutions to this inequality, which is why I will call this my solution region. All right? That means that any point in there is a solution to this inequality. And you can test that out by picking a point that's in there. I'm going to pick one like 0. That means if I plug 0 in for x into the original inequality, I get a statement like that. 0 minus 7 is negative 7. And negative 7 is indeed less than negative 2. It made my inequality true. Let's pick one that doesn't up here in my non-solution region like 6. 6 minus 7 is less than negative 2 if I plug it in. Well, 6 minus 7 is negative 1, and that is not less than negative 2. That is not correct. It did not make my inequality true, which is why 6 is not in my solution region. If you're ever not sure if you went the right direction on your number line, you can always test a point on either side. The part that's shaded should make your inequality true. The parts that's not should not make your inequality true. All right, and if you're not sure whether or not to fill it in or not, well, again, if you filled it in, you're shading it. That means it's a solution. Here, 5 is not shaded, so watch what happens with 5. 5 minus 7 is less than negative 2. Well, no, because negative 2 is not less than negative 2. Negative 2 is equal to negative 2. That also did not make it true. All right, let's move on. I'm going to jump through to our next example, because now our next example shows us how solving an inequality can be slightly different from solving an equation. We've drawn our line down the center, and as we did before, we're going to get all our variables to the same side. All right, and I'm going to move everything else that is not that variable to the other side. But at this point, we come to a step that we didn't do the last time. When we divide here, we're dividing by a negative 5, and that's the key. All right, we are dividing by a negative 5. If you ever multiply or divide by a negative, we're going to do something special here. If you ever multiply or divide by a negative, it makes everything the opposite. In an equation, while the equal symbol, whether you flip it or not, doesn't change anything. But here, this inequality symbol needs to flip to the other direction. Anytime you divide by a negative, we will flip that symbol. Turn it right around. Because it makes everything the opposite. And that's going to give me my new and final statement here, where I now have m is greater than or equal to 2. That's my answer there, and I can draw that on my number line. Giving myself my 3 tick marks, put 0 in the middle, reference point on one side, it's opposite on the other. In this case here, it's equal to, so it is going to be a closed dot. All right, and this also shows me the direction I'm going, which is this direction here, everything greater than, and so I'm just going to shade in this section here. I'm showing you how you don't have to use a different color. You can just make it darker and thicker so that we see which direction you're actually going. All right, let's take a look at a few more examples here. All right, in C, we draw our line down the center. We solve as usual, getting P alone. So I'm going to add 2P to both sides. So 2/3 P is greater than -2. And to get rid of a fraction, you could divide by 2/3. I prefer to multiply by the reciprocal because that is the inverse. I multiply by the inverse, and the multiplicative inverse will cancel each other out there. What I do on one side, I have to do on the other. These cancel each other out, giving me P is greater than. I did not flip my symbol because I did not multiply by a negative. I know that right here that 2 is a -2, but that's not what I'm multiplying by. The number that I multiplied by on each side is 3/2. That was a positive. All right. So in this case here, it still gives me a -3 as my result. All right. And I find that P is greater than or equal, just greater than -3. So I draw my 3 tick marks, 0 on one side, reference point on the left, negatives always on the left, positives on the right there, and it's going to be an open circle here because it's not equal to, and it's going this direction. So I'm going to shade in everything up here as my solution region. All right, let's take a look at the next one. D. Draw my line down the center. This time I've got parentheses, so I've got to distribute. And I've got to combine some like terms. And get all of my x's to one side. In this case here, I'm going to subtract x from each side. I like moving x to the left when I'm solving inequalities. I'll show you why in a moment. All right, but it wouldn't be wrong to do it the other way. Subtract my 5. But I also wanted to emphasize right here, I'm dividing by a -4. So what am I going to do with my symbol in the center? I'm going to flip that symbol. All right, giving me x is less than or equal to 3. All right, I just want to show an alternate route here for a moment. Some of you in this step would have done something differently. Instead of subtracting x from each side, many of you probably would have added 3x to both sides, giving you 5 is greater than or equal to 4x minus 7. I'm going to show you that that's not wrong. All right, it's okay to do that. I'm going to add then 7 to both sides. You're going to end up with 12 is greater than or equal to 4x. And when you divided, you would not have divided by a negative. You would have had 3 is greater than or equal to x, which is true. All right. But in order to get from here to here, because I want my x on the left in these statements, I would have to flip the entire thing, which would include the symbol. So you're going to end up flipping that symbol either way you go here, so that when you get to this number line and I draw my reference point, a nice solid point there at 3, I know that this symbol right here is telling me I'm going this direction because x is on the left. That only works if x is on the left, all right, because I'm saying that x is less than 3 or x is to the left of 3. All right, now let's take a look at 2 unique examples here. All right, in these examples here, I'm going to start by solving them as I normally did. I've got some like terms to combine, giving me 9k minus 3 is less than or equal to over here. 9k minus 3. Some of you notice I've got the same thing on both sides, but let's continue to solve. Let's move our variable all to the same side. Giving me negative 3 is less than or equal to negative 3. And we've come to this problem before when solving equations. Our variable drops out. And when that happens, we've always asked ourselves one question. Is this true? If this is true, all right, then it will always be true, and we go for all real numbers. All right, if this is not true, then it will never be true, and we go for no solution. So in this case here, what do we have? Well, negative 3 is less than or equal to negative 3. Well, negative 3 is equal to negative 3. That's allowed. Therefore, k equals all real numbers. I want you to notice something. I changed my sign here now. It's no longer an inequality. It is an equal sign. All right, because the value of k can be anything you want in the world. The left side of this inequality will always equal the right side, and therefore this statement will be true no matter what the value of k is. K can be anything. Still an infinite number of solutions, but k has no bound in any direction. Let me give you a few other examples of things that would also be true, and you would conclude all real numbers. Let's use the same problem. Let's just say for a moment that I got on the left side that negative 4 was less than or equal to negative 3. Well, is that true? Yes, it is. Negative 4 is less than or equal to negative 3, and so we would conclude the same thing if we had that. All right, if I said negative 5 is less than or equal to negative 3, also true. Negative 14 less than or equal to negative 3, also true. Any of those would all make the same exact conclusion that k could be all real numbers in this situation. Let's take a look at our next one over here with f. Draw our line down the center. Notice both sides are equal again, but let's do this out. Let's see what happens here when I subtract 3y from each side. I find in this case I get 1 is less than 1. And I ask myself, is this true? And before, when we solve equations and you had the same number on both sides, you went to all real numbers. But that's because they were allowed to be equal to each other. Here, there's no equality allowed. We want the left side to be less than the right side. 1 is not equal to, 1 is not less than 1. It is equal to 1. This is a contradiction. Therefore, it is not true. So y equals null. There is no solution that will make this inequality true because it will never be true. The left side will never be less than the right side. It'll be the same. All right. Other things that would also make to this that would come to this conclusion. Let's just pick a few more examples here. What if I said 2 was less than 1? Well, that is also an untrue statement, and we conclude no solution. 3 is less than 1. 4 is less than 1. All of those would be untrue statements. Any untrue statement concludes no solution. So when you ask, is this true? You either answer that question by saying, yes, the statement's true, and therefore your variable is equal to all real numbers. All right, whatever the variable is, in this case over here, we'll just use x. All right, or the answer to that question is no, it is not true, and it will never be true. And so that's when you say there is no solution, or x equals null. All right, it's the answer to this question here that makes you go one route on the other. All right, and make sure you do that with inequalities because it looks just slightly different than it does in an equation.